new solutions have emerged. For example, directive-based models like OpenMP or OpenACC, C++-based libraries like Thrust or Kokkos, and the evolution of C++. This led us to a key question. Does the C++ standard parallelism, or also known as STD-PAR model, offer a good compromise between performance, portability, and productivity, especially when running a large-scale plasma physics simulation on a single GPU? That's why we took a common method used in physics called particle and cell methods, and we wrote it using STD-PAR. We then compared its performance with two other well-known parallel programming models like Thrust and Kokkos. All three were tested on GPUs from different vendors with and without unified memory. The goal here was to evaluate how well STD-PAR performs and how portable it is across hardwares and what trade-offs it involves. I will present to you STD-PAR. So it's designed to integrate parallelism directly into the C++ language without needing any special extension, nor directives, nor external libraries. It uses familiar objects like vectors, and it follows the same memory model as standard C++. Finally, the memory management is implicit, which reduces complexity for the developers. Since C++ 17, the C++ standard introduced execution policies. It introduced four: the sequential one, the unsec, which indicates that the execution may be vectorized, the parallel STD execution PAR, that indicates that the code will run in parallel using multiple threads, and STD execution PAR and sec, the code will run in parallel with vectorization. But these policies don't specify the hardware like the CPU or the GPU. They just describe what the code should try to do. And it's based on the compiler to choose how to execute this algorithm. As we know, C++ provides a unified memory model on the CPU, allowing access to different memory regions like stack, heap, static data, without differentiating between underlying physical types of memory. But the CPU and the GPU have separate physical memory and address spaces, so programmers must manually transfer data between them. And to simplify this, NVIDIA introduced unified virtual memory, known as UVM, which creates a shared virtual address space between the CPU, the host, and the device, the GPU. AMD also has recently implemented a ROCm STD-PAR, so it's built on LLVM and integrates with AMD ROCm ecosystem via the ROC Thrust library. It supports also unified memory, but unlike CUDA, it relies on heterogeneous memory management, also known as HMM, and on XNAC. We can compile our programming, our program or our codes on NVIDIA GPUs by using the flag STD-PAR, or on CPU using STD-PAR equal multi-core. And we have to use the NVC++ compiler. For the AMD GPUs, so we can use Clang compiler, and we have to add the flag heap STD-PAR. What about MiniPeak? MiniPeak is a mini application. We have written this mini application based on Smiley, which is a simulation code for plasma physics. We use particle and cell model, and our goal was to explore new programming models, and especially parallel programming models. Several programming implemented are Cycle, Thrust, Kokkos, OpenMP Target, and OpenACC. We have a domain that consists of two data structures, particle and grids. It's a C++ code, and we don't use yet distributed memory parallelism. So when implementing Minipig using SCD-PAR, I took into account the challenges and specific issues of each operator before adapting the code. At the start of the simulation, particles are initialized. Then we enter in the particle and cell loop. And here I'm presenting to you the main physical operators. First of all, we begin with the interpolation. So it calculates the value of the global electromagnetic fields at each particle's position. Particle axis is contiguous, but grid axis here is unordered since the particles are not sorted. So this can lead to cache misses. The second step or second operator is the pusher one. It updates the momentum and the position of the particles based on electric and magnetic field. Here, the particle axis is contiguous. Each particle is updated independently, so it makes it easy to parallelize and port to GPUs. The third operator is the projection. So as particles move, they generate electric currents. These currents are calculated per particle and projected onto the field grids to update current densities. This operator is the, the most important in the loop because it handles atomic operation. So that's why before implementing the final version of this operator, we have done a preliminary study on different atomic reduction functions on GPUs to know which the one is the better to use. And the final main operator is the Maxwell solver. So once the current densities are updated, the electric and magnetic fields are computed using Maxwell equation. The step is a stencil problem, and in our case, we have a large number of particles, so this part becomes relatively lightweight, and it parallelizes well on GPU. For example, in our benchmarks, the Maxwell solver and boundary conditions account for only 5% of the total runtime, making them negligible compared to other operators. The methodology, so in this work, we compare three ways to program GPUs in parallel. So we mainly focus on thrust, which is the backend used by SCD-PAR in NVIDIA, and by AMD through ROC thrust since ROCm 6.1. We also look at Kokkos, and to be able to understand how memory management will affect performance, we tested both Thrust and Kokkos using unified virtual memory because SCD-PAR by default uses UVM. And we have done the tests on multiple GPU vendors like NVIDIA V100, A100, H100, GH200, AMD MI250X, and 300 MI300A. Here, as you can see, we have the benchmarking results. And to be able to identify the performance bottlenecks, we performed a roofline analysis using a NVIDIA Inside Compute on V100 and A100 GPUs based on 40 iterations of Minipig loop. The analysis reveals that the performance of the kernels was limited by the memory bandwidth, indicating that our kernels are memory bound. And to ensure fair comparison across different GPU architectures, we evaluate performance using a normalized metric. It's the number of particles processed per gigabyte of memory, which is calculated as the number of particles computed per seconds, divided by the memory bandwidth. As you can see here, Kokkos and Kokkos UVM deliver nearly identical performance across all GPUs. They remain stable even with increased memory usage. Thrust and Thrust UVM show similar behavior. We have we don't see this behavior on NVIDIA A100, but it's a small difference. It's about 8%. On um, for example, we have STD bar. It outperforms thrust UVM by 16% on the V100s initially, but this advantage drops to 3% at higher memory usage. On A100 and GH200, it lags behind by 10% and 25% respectively. So overall, we can see that thrust UVM is always a little bit behind Kokkos in performance. SCD Power is a little behind thrust and thrust UVM in performance. But for example, on the H100, SCD Power performs especially poorly, achieving only the half throughput of thrust, while thrust UVM, Kokkos and Kokkos UVM remains stable. So right now, we are investigating the cause and have already ruled out several possible explanations. For example, thrust UVM has a stable performance, so that suggests that UVM is not the problem in our case. If it were, thrust UVM would also show the same issue. Also, although the GH200 offers 20% more memory bandwidth, this alone cannot explain the 50% performance gap that we observe. For AMD GPUs, the MI250X shows declining memory efficiency across all models as particles per cell increase. Kokkos, Kokkos UVM, and Thrust perform best, while Thrust UVM and especially SCD-PAR degrades in performance. So for example, as you can see, SCD-PAR drops to around 1000 particles per gigabyte. This can lead us to say that on MI250X, the UVM handling is poor for thrust and SCD-PAR models because Kokkos UVM didn't show the same problem. But on the MI300A, we have a clear improvement. Performance is very stable across particle counts. Thrust UVM no longer suffers and SCD bar improves. But it's still behind. But overall, we can say that the MI300A delivers better and more consistent memory efficiency, with Kokkos leading, followed by Thrust and a much improved SCD bar. These performance results that we have saw are strongly influenced by the projection operator, and it dominates the total runtime, as I mentioned earlier. So if we look at this slide, you can see that the percentage of time spent in the projection increases with the number of particles per cell across all architectures and backends. So as the particle density increases, projection accounts for 50% to over 80%. And that's why we were motivated to do a small test to test the reductions, the atomic reductions on GPUs using, for example, the typecast to a STD atomic, or using STD atomic ref, or the native CUDA atomic add. And we have concluded that the atomic add of CUDA is the most performant on GPU, but this causes lack of portability across GPUs. So to conclude, here are some key strengths of the approach that we explored. First, we can say that SCD-PAR is accessible to non-experts, making it easier for developers who are not familiar with the GPU programming to adopt. There is no need for major rewrites of the existing C++ code. It also offers automatic memory management, so developers do not need to handle memory transfers manually between the host and the device. Another important advantage is that it's compatible with NVIDIA and AMD GPUs, which are widely used in HPC environments, and it supports classic dynamic memory allocation, which can simplify development for more complex data structures. And finally, it delivers high performance for simple loops, which are common in scientific workloads. Despite the strengths presented earlier, there are still some limitations to consider. First of all, the current approach offers limited optimization opportunities for expert users, for programmers who want to have a very performant code on a specific architecture. Also, the CPU-GPU switching without explicit data management can lead to inefficient data transfers, which impacts performance negatively in some cases. Another point is that the execution policies are tightly coupled with compiler support, meaning that the implementation and behavior may vary depending on the compiler. In addition to that, the model is still under development, so some features are not fully mature yet. That being said, there's a clear potential for further improvement, both in terms of optimization and broader hardware support. So looking ahead, we want to investigate the performance differences between different programming models, particularly in comparison with Rust. We want to analyze the performance variation between the NVIDIA GPU 800 and GH200. And as users, we may ask whether a more flexible API is capable of offering finer control over optimization, or it will be complex as the low-level models like CUDA. Can smarter internal strategies such implicit asynchronism could make a CD-power better effective tool for HPC? Might the upcoming sender-receiver abstractions in C++26 offer a more practical and a portable way to express asynchronous execution, improving both ease of use and adaptability across architectures? To answer this question, we need to do further studies. That's why, in this context, we will continue to explore how best to balance between usability, performance, portability, and productivity in scientific computing. Knowing that we have time, so I had a slide that I wanted to share with you. This is the results that we had while doing our preliminary study. So we have done a vector, and we have done reductions on this vector, atomic reductions on this vector, and we have used different approaches. For example, we have used the SED atomic graph on NVIDIA GPUs and AMD GPUs. As we can see, the SED atomic graph and the typecast to SED atomic while using SED power gave us a poor performance. But when we have done atomic add, when we have used CUDA atomic adds with SED port, Thrust VVM, Thrust, and Kokkos, we had much better performance. Just to be more precise, with Kokkos we have used the Kokkos atomic adds, so this is a more portable solution than the atomic adds, than the CUDA atomic adds. As you can see, we had much better performance using atomic add in the projection loop. But we have the same problem with the AMD MI250 we had a poor performance that can explain why in our tests we had these results, these results for MI 250, but on the MI 300 we had much better results. Thank you, and I'm here to answer for all your questions.
Thank you very much, Esther, for this great presentation. And I think we already have a question with Damien.
Esther, could you go back to your result with the atomics?
Yeah, this one?
Yeah, this is a bit nuts. I'm wondering whether I don't remember on top of my head what implementation of pseudoatomic and pseudoatomic refs they have with the NVIDIA toolchain, but it really looks like even though it's kind of a hidden parameter and it's not something that exists in the standard, the notion of scope. So what other threads can see your atomic updates? But the fact this is so big, I wonder if they're being very, very strict and using something like system, whereas the atomics in Kokkos only have a device scope. You should probably look more in detail what they have underneath the hood and see whether you're really comparing apple with oranges. Yeah.
Okay.
Yeah. So if you look in the NVIDIA documentation on their libq std or whatever, look, there is a trailing template argument on the atomic thing, which is called the scope. And double check what they use by default. I bet with you that they're using something that's larger than what we do in Kokkos or what the atomic head is, and that's probably explain why it's different. I'm kind of surprised that it's that big the difference.
Okay.
On this point, I agree with you, but that means that the conclusion of Esther is valid. The C++ standard doesn't specify things that are grain fine enough for GPU computing. With this, there is no concept of device, or there is just a concept of a parallel loop. And if you say atomic, what happens in the parallel loop should be seen from outside the parallel loop. If you want to go further, you need something that has a more fine-grained API, and that's what Esther said in the presentation.
Sure. Sure, but you could go further and specify the things that can't be represented yet by the standard and confirm that this is where the difference come from, and then you can dream and things that you can convince the committee to introduce the notion of scope. But at least it would explain where the difference is coming from.
Thank you. We have another question, Matt B.
So, question for you. When you're doing the difference between thrust and stood par, what data containers are you using for thrust
Vector.
and stood par?
Device and host vectors. And for SCD par, we are using SCD vectors.
There is it's a known issue that casting stood par standard vectors to restrict pointers prior to putting them into these loops greatly improves performance. And stood par is built for NVIDIA on top of thrust. If you look at the function call stack, you'll see thrust calls in there. So it's most likely in the interpretation of the standard vector versus the thrust vector, which is the difference. So a good experiment would be to take the standard vector that you use in stood par, cast it with the data operator to a restrict pointer, and then iterate over that and see if your performance comes up to par.
Okay.
There's a lot of assumptions with standard C++ that don't operate well with the parallel loops. And like the atomic issue, which I agree with the previous comments, it's probably scope device, not scope device, but scope system, that you have to make certain assumptions to be, quote, standard compliant that are reduced when using libraries like Thrust or using libraries like Kokkos. So to do true apples to apples, you need to make those assumptions consistent.
Okay.
Thank you. Do we have other questions? Yes, Damien?
So I was wondering whether you tried playing a bit with the number of particle when you do this comparison and see what you can achieve, but it would imply doing more thing with Kokkos. So I don't know if you would ever care to implement a CUDA version, because there's one limitation with the standard at the moment, what it provides you, which all the parallelism you can expose with the logic you have right now is the number of particles, for instance. And to saturate a GPU, a modern GPU, you're going to need the order of at least 200,000 particles. But that's one of the challenge, right? When we handle matrices, when we do finite elements and when we do particles and things like that, we don't always have enough. And that's where Kokkos, if you go to hierarchical parallelism or CUDA or SQL, will give you other constructs that will let you expose more parallelism. So, for instance, you'll be able to use some parallelism on your number of neighbors or whatnot, or if you are doing finite elements, number of quadratic points. So I think you should consider in your work comparing, like looking a bit how that behave when you don't really have enough to saturate the GPU, and have a more complicated implementation in CUDA or in Kokkos that shows that you can achieve much better performance with these programming models, and that the standard need to evolve to be able to expose more parallelism. And what you have at the moment proposed for C++26 with pseudo executors, standard receiver, doesn't help you at all with that at the moment.
Yes, so yes, we are willing to rewrite the code using CUDA while doing fine-grained optimizations, and we are willing also to write it using CUDA stream effectively to do that comparison with the STD board.
Thank you. Are there any
When you look
other...
into this fine-grained optimizations with CUDA, look at the code pick on GPU or WarpX, because they do local, for your projection algorithm, they do local tiling of the particles. They push those into shared memory, have fast shared memory atomics, so not even device scope, but shared memory scope, and then do a single push from those projected currents down to the device level. And that gets them basically limited not by the atomic performance at all in these. So it's in the L1 performance is their limiter. So they can get a lot more performance out of that.
Okay.
Any other question? Well, I do have one. I was wondering, do you know if it's possible to nest parallel algorithm? I mean, in the standard, there is nothing that prevents it, but in the implementation from NVIDIA and from AMD, do you know if you are able to have two parallel algorithm nested one into the other?
I don't know, and I haven't tested it.
Not from NVIDIA, sorry. It comes up in discussion. I bring it up in discussions, put it that way.
I wonder actually if it's, Kokkos, we improved a bit our diagnostic, but I'm kind of curious to see if you play doing a parallel for and you force host execution and you nest inside parallel for on the GPU, whether it's thread safe and what happened.
That's something else.
Yeah,
The C++
yeah,
standard, it's not parallel. It
yeah.
means your code is safe to be parallelized. It doesn't say run it in parallel, which is kind of different
The
semantics.
standard doesn't allow you doing it.
Okay. Okay. And I have a question on this this slide. So on AMD, we see that on MI250X, thrust and std_par are very close to each other, which would point to the implementation of std_par being based on thrust. That's not so much the case on MI300A. Do you know if you've observed the different, what would point to different implementations, or do you have any idea about where that comes from?
For now, not. We are looking why we have this difference, and we are looking also why we have this fluctuation for std_par. As you can see, the points are fluctuating, and for now, we don't know what's the main reason behind. So it's to be more explained in the future.
Okay. Thank you. Thank you very much. Any other question? If not, let us.
So sorry.
Oh, yes.
Have you ever compared the performance with their native language like HIP or CUDA? Because I'm wondering in Kokkos performance is identical or very close to that or not?
In CUDA, no, we are implementing right now the code in CUDA.
Okay.
Direct answer to you, Ichi. You may play with it, but you're not going to discover anything wonderful. If you have an optimal thing in CUDA or in HIP, at best, Kokkos is going to match. And if Kokkos beats CUDA or HIP, it means that you didn't actually implement it well in CUDA and HIP. But there's nothing special to discover if you do that.
Well, actually, it's coming from the story from my collaborator, and he's working for some sort of protocol called probably NVIDIA code, and he got good performance on NVIDIA GPUs, but not for AMD GPUs. So in protocol code, you may encounter something like that. That's what I have in mind, but I'm not sure.
Thank you. Okay, so let's us all thank you again, Esther, for this great presentation, and we should see us again on the 18th of June for our next Kokkos Tea time. It's not been announced yet, but it should be very soon. So see you on the 18th of June. Bye-bye.
Thank you so much. Bye.
Bye.